So in the videos about the query optimizer, we looked at how to translate a declarative query to a query execution plan, a physical query execution plan. But once we have this here, we still do not know how to actually execute it, because what we determined so far was whether to use an index or not, which join order to use, which specific join algorithm to use, stuff like that. But there are still many options on how to execute this plan. And that is what we look at in this video. So again, so far, this is what we did. Declarative query translated to this physical execution plan by the query parser and query optimizer. But there's another mapping from this plan. Let's put it on the left here. So from this physical execution plan, how to execute it. We map it again to some physical structure. We map this to a program, in other words. But how does that program look like? So one straightforward interpretation of what we have on the left here is to say this is a call graph of the different functions, where each function here is one of the database algorithms we looked at in the previous video. So basically, this means we have a scan function scanning this specific input relation, then it outputs the data belonging to C, then that data is the input for this sort function, which sorts the input with respect to this attribute, outputs the sorted relation C, and so forth. Here this merge join takes two input parameters. One is the left input, the other is the right input, and then produces the merged output, of course. So this is just a function tree of our physical execution plan. So basically, we interpret it as follows. Here, I just flattened it. So here, this is the same call graph, which is a tree in this example. So this is just a flattened tree. That's the same expression as above here, just written out in one line. But this has one drawback, because we don't really know what happens in between those function calls. How is data passed from one function to the other? So in standard programming, if you pass data from one function to the other and only have few function calls, there's no issue in passing some data around. But here, the data might be potentially big. So for instance, if C has 1 terabyte or gigabyte of data, and you actually materialize it before passing it to the sort function here, that induces some costs. And that holds for all other edges here in this graph. Whenever you pass large chunks of data from one function to the other, this involves some cost. So whenever you produce something here, this is called an intermediate result. And we see it again if you zoom in into the graph. So here, if you make the assumption that C has originally 1 terabyte, B has originally 1 terabyte, so we don't filter anything here. Of course, this means this intermediate result that is passed from this function to the next function above is also 1 terabyte. Only here we filter, and then depending on the selectivity, let's assume maybe we only have 1 gigabyte of data here. Here, scanning returns 1 terabyte, of course. Sorting doesn't change the size of the data. There's another 1 terabyte being passed here. Then the merge join here depends on the selectivity of the join operation. Let's hope for the best. Maybe it's just like 10 gigabytes that are passed up here, but still that's a lot of data. So if you really materialize that in one chunk, that might be way too expensive. Here, this is a little better. So maybe here, this seek operation where we really exploit the index. Let's assume it's super selective. Maybe this is just 100 megabytes. So this is not going to hurt that much. But still, you see a lot of data is being passed around if you naively materialize the output of each and every function call. And this may also mean if you don't have this space available in main memory, let's go to this example here, maybe you have to split it to disk. So this might imply you can't pass the data directly to the next algorithm here. Maybe you first write out 1 terabyte to disk, or to SSD, or whatever persistent medium you have. And then you read it again here in order to be able to perform this operation. So this may trigger a lot of costs. Still, some systems actually do that. So some systems fully materialize the output of the different functions. Even main memory systems sometimes do that. And then what they do is, okay, if I have a large output, so whatever I delegate the responsibility for handing that to the operating system. And then the operating system has to cope with handling 1 terabytes of data. It will start swapping it to hard disk once it's overflowing the available memory, and then it's reading it back. So, however, this materialization of intermediate results, this full materialization of intermediate results, is really problematic and may lead to costs that can be avoided easily. Therefore, we want to look at another mapping, and that is to introduce some sort of pipelining. Pipelining occurs in many places in computer science. Maybe you know it from the Unix shell already, those pipe symbols. If you have something like Unix or Linux, then you have something like grep, whatever. Then there's a string, and then you can pipe it with this symbol. That's a pipe symbol in Unix. Pipe symbol. You can pipe it into another command. You could say, for instance, do another grep if you wanted, and then you do whatever here, and then whatever, you write it into a file, out.txt. This can nicely be done in Unix and Linux, of course. So it's a similar idea we're following here, but it's not exactly those symbols. That is not what I'm talking about in the following. What I'm talking about here is the general idea of pipelining. So we're going to discuss that on a higher level to start with, and then go down to the different options. Because actually, in order to implement pipelining, there are many, many different options. This is just one of that. One of those options is implemented in Unix. And we will discuss different implementations of pipelining in this video, in this lecture, in the following videos. So for the moment, I will discuss pipelining on a higher level, the general idea of pipelining. What does that imply? So let's zoom in and let's go back to this execution plan we had in the beginning, and basically how you could imagine that. Here we have inputs at the bottom. We have 3 inputs. They're like water sources. And you want to pump the water up to the output. This is the output. Those are the results, of course. Here on top, that is the result of the specific query you want to execute. Here at the bottom, you have the inputs, the sinks, the data sources, or let's call them water sources for the moment. So we have 3 of them. So pipelining can be visualized by depicting it with pipes. That's what I did here. Those are water pipes. And then you see there are specific operations going on. So for instance, here you see there's a sort operation, sorting the input. Here the filter filters out some of the input water, just some of the water drops get through. Then here this merge join, of course, combines 2 input pipes into 1 output pipe. The same is done by the simple hash join, though using a different method. So, however, if you visualize pipelining like that, this is an oversimplification. This is ignoring what's going on in the pipeline, what's actually going on in the pipeline, because what's going on is something like this. We need to show the pipeline in more detail, because depending on the operation, on the algorithm you're using, some of the algorithms add extra water tanks. So let's start with a simple example. Here's a sort operation. It's not that the water flows through this operation. What sorting does is it first consumes all of the input. All of the water is first buffered in this water tank. Only if the last drop of water was stored in the water tank, then the actual sort operation takes place. And after sorting, or at least once you identified the first element in the sorted sequence, you are allowed to pass the water on to other operations. Sorting can only be correct if you inspect each and every input. To go back to data, and let's forget about water for the moment. If you have a sorted sequence of data, how can you make sure to return the smallest? Well, you first have to look at all of the data. You have to make sure that you've seen all the data. Otherwise, it's impossible to pass out the smallest element. And it's the same problem with water. Yeah? So you first buffer all of the input. All of C is going to be buffered here in the water tank, and then it's passed on. The same happens in a simple hash join. The simple hash join bulk loads a hash table on the left input. That happens here. Only after all of the input was read, then the right input can be probed against that water tank, which happens to be the hash table in that example. And only then we are going to produce join results by passing out data here. So what this means is some of the operations actually block the flow, block the water flow. They are pipeline breakers. That is what we're talking about here. This is a pipeline breaker. Here, sorting is a pipeline breaker. And this simple hash join is a pipeline breaker because it buffers all of the inputs. Sort buffers all of its single input. It's a single input operation. Simple hash join buffers all of the left input. As we have an index seek, it's likely that the amount of data we're buffering here is not so big compared to the entire relation C here. It depends on the concrete sizes, but if we use the same numbers as above, if this is 1 terabyte of data, we have to buffer 1 terabyte of data here in this operation. And that's a lot of data. So you maybe want to worry about how to buffer that efficiently. So let's look again in some detail into those operations. How are those valves set? So if you look at the different stages of simple hash join or index nested loop join, assuming that the index does not exist yet. It's a different story if you already built those indexes, be it a hash table or any other index. Look back at my videos explaining those algorithms if you're unsure about that. But here we assume that the index does not exist yet. So what happens here in the first phase is the valve is set like that. So all the water or the data streams in and is buffered here. So buffering may imply here that you do a tuple-wise insert into the hash table or into the index. It might also mean that you first buffer all of the data, you just store it. Notice that those valves are closed. Nothing is happening here. Everything is blocked with respect to the right input, and no output is produced at this point in time. So as long as data is streaming, nothing is going to be produced by this operation. Eventually, the left input is exhausted. No more data is available here. Then we have seen all of the data. And then again, depending on whether you already did a tuple-wise insert into the index or not. So if you already did a tuple-wise insert, then the index is ready for the next phase. If not, you need to bulk load here. Yes, option A, let's call it just buffer. Or option B is tuple-wise insert. And then if you're here in option A, if you just buffered, you bulk load the index, of course. Bulk load the index. In option B, you're basically done already. Yeah? The index is already there. And then in phase 3, you can open these other valves. You could say, okay, now I let the right input stream against my index here and probe it. Yeah? So every tuple here is probed against this buffer, against the water tank, and when there's a result, if there's a result, you output it here, you send it here. That's the idea. So in A and B, it's the same. It's an index probe. We looked at that already in the different videos on simple hash join, index nested loop join. Here again, just separating the different phases of those algorithms by showing, okay, there's this phase 1, which is really, really blocking. This is blocking the pipeline. This is blocking. This may be longer or shorter, depending on whether you are in option A or B. And this is really non-blocking. This is a non-blocking part of the algorithm, okay? And we can do the same for quick sorting or any other sorting algorithm. Let's do it first for quick sorting. So in quick sorting, again, there's this phase where you read all of the data. You accumulate it into some main memory array, for instance. Then you actually sort it. That is when you call quick sort. And here you actually output it. That is one way of splitting up quick sorting into those 3 phases. Again, this is blocking, this is blocking, this is non-blocking. Let's write it down again for completeness. Blocking, blocking, non-blocking. Okay, so let's look at external merge sort. We also discussed that in separate videos. Here we have the same three phases. So again, there's this reading phase. However, here already you generate those runs. Here you do the run generation. Nevertheless, this is blocking. No data is being produced. Then there's the merge phases without the final merge though. So you keep on merging until you are able to execute the final merge. But while you're merging, while you're not in the final merge, you're blocking. Nothing is going to be produced by this algorithm. And then finally, once you are in the position to execute the final merge, then you are non-blocking. Non-blocking. Yeah, this final merge, we also called that the online merge, online merging. The last merge of the merge tree can be executed online, doesn't have to be materialized. So those are the phases of external merge sort. So here I try to depict the different building blocks we have seen so far. So here we are on the blocking side, here we are on the non-blocking side. And well, let's start with the easy cases, projection and filter, of course. Those are definitely non-blocking. So here for the filter, for instance, one tuple is the input at all times. And then, of course, the filter may output that tuple or may not output. So 1 goes in, 0 or 1 goes out. For projection, 1 goes in, 1 goes out. That is the rule here. Yeah, then let's start with the blocking operation. So here we had this in the previous slides. So here the index nested loop join and the simple hash join and the bulk load and the sort. So actually we could say this is the same thing because sorting is a variant of bulk loading. Yeah, those are very related. So if you only look at tree structured indexes, you could say that bulk loading a tree is a variant of sorting. There are interesting papers about that actually. Sorting, on the other hand, is a variant of bulk loading a tree. You see the relationship. If you sort an array, of course, this can directly be exploited for a binary search. So basically, it's the same idea. Depending on the specific algorithms, they're both creating an index structure in a way. Yeah, then here index nested loop join, I think it's important to understand that this is a combination of two things. So you could say, actually, this is a bigger molecule, so to say. The atom is more something like this. So we could write it like that. We could say this INLJ / SHJ, index nested loop join / simple hash join, is basically just a bulk load plus this one here, which is index nested loop join, simple hash join without bulk load. There was something we had seen before. I said in those videos, and I said it in this video as well, if the index already exists, the entire algorithm is non-blocking because you can directly probe the right input against that index. There's no blocking anymore if the index already exists. So you could also phrase this as index probe. Index probe. This is non-blocking. So this is the index nested loop join with bulk load. And this is just a combination of those two. It's bulk loading plus this index probe. So this one here, that is the index probe, which is non-blocking. That is how you can decompose those different operations. So here are a couple of other operations. Of course, a merge. We've seen a merge in the context of external merge sort. Again, the fan-in here is depicted as 2. Here it's 2. Yeah, those are the inputs, that's the output. But it can be anything. It can be anything greater or equal to, that's fine, depending on the performance considerations. But still, this is non-blocking. The same holds for a merge join, where both of the inputs are already sorted. Even if you take more than 2 inputs, usually we only look at binary operations here, but even if you take more than 2 inputs, This is a non-blocking operation. Yeah, and then interestingly, we had this algorithm as well that's called the double pipelined hash join, or to be more precise, you can generalize that to be the double pipelined index join. So we had a separate video on that. This is non-blocking as well, even though it has 2 water tanks. But the interesting property of this algorithm is this idea of taking one tuple here from one input, putting it into the water tank, and then probing it against the other. If you already find some join result, you output it directly. It's not like you close one input and then finish processing the other input first. So we have something like that here. You just process the left input entirely and then you start probing the input on the right. That's not what's happening in double pipeline hash join. So in double pipeline hash join, really you process both inputs more or less simultaneously, and therefore this is non-blocking. So those are important building blocks you find in query execution pipelines. And so notice that I say query execution pipeline rather than query execution plan. So now we identified those different components that we find in the query execution pipeline, not the query execution plan. The query execution plan now was transformed into a query execution pipeline. Still, we have many options on how to get from such a component to actual code. And how that works, we will look at in the following videos. If you liked this video, don't forget to hit the like button. Thank you. So if you want to see more database videos, be it in English or in German, take a look at my website datenbankenlernen.de. It has a couple of English and German videos. You can also subscribe to my YouTube channel, Jens did, or you look at our website infosys.uni-saarland.de. See you there!